Howdy, today on Flipping Science we're talking about tripolyphosphates. So you need to be able to describe how the reaction of soap with hard water differs from that of synthetic detergents, draw the structural formula of the phosphate ion, and draw the structural formula of linear and cyclic tripolyphosphate ions, explain how tripolyphosphate ions keep calcium and magnesium ions in solution, clay particles in suspension, and pH mildly alkaline, explain the importance of tripolyphosphate ions, and describe advantages and disadvantages of the use of phosphate fertilizers and tripolyphosphates in detergent formulations. So soap has a bit of a problem in that when it reacts with dissolved calcium and magnesium ions, you get a insoluble carboxylate salt called Scum being produced. You get high concentrations of calcium and magnesium ions in hard water, which is quite common. Adelaide, for example, has very hard water because a lot of our water comes from the Murray and there's a lot of limestone cliffs there, so you get a large calcium ion concentration from the limestone that makes up the cliffs as it dissolves into the water. So here's an equation showing the scum formation. So we have the calcium and magnesium ion dissolved in water, we have the carboxylate salt, which is the soap, and as they react together you get the solid insoluble scum forming. The problem with scum is you're removing soap from the cleaning solution, so you have less soap available to do cleaning, and also the scum comes out of solution, it precipitates out and it forms on clothes or on, in your shower, for example, you might have scum forming, and it's unsightly and it stains your clothes and it's not good. So scum isn't good. Synthetic detergents, however, don't form scum. So the calcium and magnesium ions, they do react with the sulfonates that make up the synthetic detergents, but the result is soluble in water. So because it's soluble in water, it just washes away. It doesn't get deposited on clothes or in your hair or in the washing machines. So modern detergents contain about 15% surfactant, so soap or detergent. The remainder is compounds that assist the surfactant to clean. And one of those compounds is called sodium tripolyphosphate. Here's the structure of the tripolyphosphate ion. You can see there's 3 phosphates, lots of oxygens and negative charges on some of the oxygens, so it's got a negative charge. This is the cyclic version, so it's in a circle. This is the linear version. They're used in cleaning agents, and we'll see why. So we'll just go back to the structure for a second. So in a linear tripolyphosphate, you have 3 tetrahedral phosphate units linked by the corner oxygen atom. So we'll start with the phosphate ion, and they link together at this oxygen to make the tripolyphosphate. With the cyclic, you have 2 of the corner oxygens linking into 2 different phosphate groups, so that's how you get the cyclic one. They're produced from sodium hydrogen phosphate compounds undergoing condensation reactions at different temperatures. So different temperatures will produce the linear and cyclic versions. So why do we add tripolyphosphates to water? Well, number one reason, they produce a slightly alkaline solution when they're added to water, and alkaline solutions are favourable for detergent action. We can see how they form a slightly alkaline solution if we have a look at this equation. So P3O10 5- plus H2O goes to P3O10 4- plus hydroxide ions. We're getting hydroxide ions produced when we're putting these things in water. It's a weak base, it's not a strong base, so we're only getting some hydroxide ions being produced, so we're only just making the solution slightly basic. So the reason why alkaline conditions are favourable is because if the solution is slightly acidic, you get the molecular form of the detergent being produced, which is non-polar. It's also non-insoluble, and it's not going to help micelles being produced. If we look at our reaction down here, it's reacting with a hydronium ion, and we're getting rid of the ionic head here, and we're attaching the hydrogen to it. So now we don't have a strong ion here. That means that we're not going to get as strong attraction with water molecules. In fact, because of the long carbon chain, it will now be insoluble, so we won't be able to use the detergent that's in the solution. Also, if the solution is alkaline, any grease that's in there, there's a chance that you're going to get some alkaline hydrolysis of the grease, which is made up of fat or oil. When that happens, you produce a little bit of soap, so that will help with further removing grease. So by having it slightly basic, we get 2 advantages. We maintain the sulfonate head, the ionic sulfonate head, and also we can start to dissolve some of the grease by doing some alkaline hydrolysis of the grease. Second reason why tripolyphosphates are handy is because they remove free calcium and magnesium ions from hard water. So remember, hard water has high concentrations of calcium and magnesium ions floating around in it. And this is good because by getting rid of the calcium and magnesium, we can prevent scum from forming. So we talked before about scum is formed when you have soap reacting with calcium and magnesium ions. So by removing the calcium and magnesium ions, we're reducing the ability of scum to form. So if we have a look at the equation down here, we can see we've got our calcium and magnesium ion. We have our tripolyphosphate with its negative charge. The magnesium ion is attaching to the tripolyphosphate because they have that mutual, so positive charge, negative charge, they're going to attach to each other. Because the hard water ion is now attached to the tripolyphosphate, it's not able to produce scum. Last reason why tripolyphosphates are handy is because they act like defoculates. They keep clay particles suspended in water rather than causing them to be settled back down. So clay particles have a negative surface charge, and because of that they bounce off of each other. They're not attracted to each other, so they bounce off of each other and remain suspended in solution. So if we have a look at the water on this side, we can see there's lots of brown in there. That's the clay particles that are repelling away from each other and staying suspended in solution. If you have calcium or magnesium or aluminium or other ions in the water, they neutralize that negative surface charge of the clay, and that means if there's no negative charge on the surface, they're not going to stay away from each other anymore. They're going to stick together, and if you get enough of the particles stick together, they'll settle out under the influence of gravity. By shoving in the tripolyphosphate ions, you're reducing the concentrations of the calcium magnesium ions that are floating around in the water, so you're going to reduce their ability to neutralize that surface charge of the clay, and that keeps the clay with its negative charge, repelling each of the other clay particles, and it keeps them in solution. If they're in solution, they're not going to settle onto your clothes as much, so you won't get those brown stains. Tripolyphosphates aren't without their problems, however. If you add phosphate to your water that you're using to clean with, that water will eventually make its way into waterways. Phosphates contain phosphorus, obviously, which is a fertilizer. It's used to help things grow. And it's also in a soluble form, which is available for aquatic organisms to use. So what happens is you get this thing called eutrophication. So what happens is the phosphorus runs off into the waterway. You have algae in the water that love the phosphorus. They see it as a fertilizer, so they start reproducing really, really quickly. As they're reproducing really, really quickly, they're blocking the sunlight from reaching plants down the bottom of the waterway, and that reduces the amount of oxygen that's being produced from photosynthesis. So photosynthesis produces oxygen. If you're blocking out sunlight to plants that are deeper down, then you're not getting photosynthesis occurring with those. If they're not photosynthesizing, then that means you're getting less oxygen in the water, and if you get less oxygen in the water, then things like the fish, which require the dissolved oxygen, start to die off. If they die off, then they're going to start to break down, and they're breaking down in anaerobic conditions because, again, there's very little oxygen available because of the amount of photosynthesis that's going on at the surface, not down deep, and then we get an anaerobic breakdown. And that can be quite problematic because we're getting things like hydrogen sulfide, ammonia, and methane being produced, and that's not necessarily good for the environment. So too much phosphate in the water leads to eutrophication, so too much algae being produced reduces the amount of oxygen in the water, and that leads to the death of other organisms in the water. So let's do some questions. The first question says, sodium tripolyphosphate is commonly used to soften water. Draw the structural formula of the tripolyphosphate ion in Na3P3O9. So the tripolyphosphate ion is the P3O9 bit. That tells me that it's the cyclic form. If it was the linear form, it would be P3O10. So let's draw the structure. So we've got phosphorus, double bond to an oxygen, down to an oxygen, down to an oxygen. That goes to a phosphorus, that goes to an oxygen, that goes to a phosphorus, that goes to an oxygen. Now we've got a double bond to an oxygen over here, double bond to an oxygen over here, and now we need to put in our negative ions. Okay, so let's count it up. 1, 2, 3 phosphoruses. Now we need 9 oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygens. So there we go. So there's the structure. The next question says, describe the potential environmental consequences of adding Na3P3O9 to commercial detergent formulations. So adding phosphorus to the detergent means that it will be mixed with water and it will make its way eventually into waterways. It's a fertilizer for algae. The algae will start to grow in large amounts. As they grow, they'll start to remove oxygen from the water, and they'll prevent photosynthesis of plants deeper in the waterway below the surface level. Because those plants aren't photosynthesizing, they're not producing oxygen, so we get less and less oxygen in the water. Less oxygen in the water means less oxygen for the organisms floating around in the water, so less oxygen for the fish, for example. So they'll start to die off. The aquatic plants also will start to die off, the deeper aquatic plants below the algae. As they die off, they'll start to undergo anaerobic decomposition, and that can be and start to produce things like hydrogen sulfide, ammonia, and methane. One other thing you could talk about in here, other than the eutrophication, is the fact that by adding the tripolyphosphate, you're going to reduce flocculation of silt. You're going to reduce flocculation of clay particles. So you're going to have more clay floating around in the water. And again, that could be bad for fish, which need to have relatively clean water flowing through their gills, otherwise they won't be able to breathe. So you get an accumulation of silt in the waterway as well. So that's another thing you could talk about in your answer. Today on Flipping Science, we talked about scum, we talked about tripolyphosphates, and why they're used in detergent formulations and their environmental consequences of their use. That's it for Flipping Science today. See ya!